Welcome everyone to the 2024 Photonic Spectra Summit Series. Thank you so much for attending the Optical Design Summit, and in this session you will hear from Frank Wierowski, the co-founder of Light Trans International GmbH. Frank earned his doctorate in applied physics and is recognized as a pioneer in the advancement of optical modeling and design software. He's authored about 200 articles covering optical modeling and design. Today he's joining us to trace the evolution of flat lenses. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me. Frank, we appreciate you taking the time to join us today.
That's my pleasure, Jake, to be with you. I now take the screen. Okay, great, then let's start. So in this webinar, my goal is to delve into the flat optics technology and investigate ways to further its progress. And I ask in the beginning, I'd like to go to the first question, is what are the anticipated outcomes of incorporating flat lens in optical design? And now I switch off my camera just to continue this. And so, yeah, to answer this question, it is useful to introduce some concepts and terms related to the topic of flat lenses. Every lens is designed to transform one or more incoming wavefronts. In imaging, it is common to transform spherical and planar wavefronts. Mathematically, the expected function of a lens is described through a list of input and corresponding output phases, also known as signal phases. And the functional lens is the object utilizes the list to execute the transformations as specified. We distinguish transformations that involve just one pair of wavefront phases, which is termed a single field transformation, and on the other hand, when multiple pairs of wavefront phases are involved, the process is referred to as multi-field transformation. So then we have a J there because we have a set of them. In a basic imaging scenario, the lens function is specified by transformation of divergent input wavefront phases into convergent spherical output wavefront phases. Mathematical form is given here. We assume now that the functional lens has specified. It means we know what kind of imaging situation we like to obtain. So the M is specified, etc. Next, the functional lens is replaced by one or more suitable physical lens surfaces that achieve the desired transformations with sufficient accuracy. Within the Parkes approximation, we all know the solution, of course. The design of the surface is resolved by a single spherical surface. Next, we go beyond the Parkes approximation for surface design, and we base it on the principle of physical optics, or one of the principles of physical optics, that the phase of an electromagnetic field remains unchanged at the interface between two dielectric media, as long as we are not in the regime of total internal reflection. This statement, by the way, is an alternative expression of the law of refraction, but it enables in this form a very elegant surface design equation, which simply states that the phase difference between the desired input or the coming input and the desired output should be zero on the surface besides a constant psi bar, and this bar can be adjusted to ensure that the surface we design by this equation intersects the specified reference point ref, for example, here to meet the stop. Now, solving the design equation for this example results in this example, it results in an aspherical surface, which is performing this transformation. The dashed lines here indicate the size of the input, and by that we can also see the thickness of the lens which we need, or which is active to realize this transformation by this blue region. The lens surface can be flattened. That means we like to make it thinner, and we will soon consider the methods to achieve this in this webinar. Now and here, I want to highlight that flattening the lens surface does not alter the distances to the object and the image planes. That means here the planes we have here, maybe by the lens equation, thereby not flattening the system itself, just flattening the lens. This blue aspherical lens surface transforms correctly for the axial field. Now let's go to an off-axis field here. Then the solution is this red one, if we use this reference point, and when we use this reference point, this one. Here, as expected, when we have two different solutions for two different fields, obviously a single surface fails to address multi-field transformations and generates aberrations for any input wavefront other than the one it was designed for. And you all know that, of course, and there will be more talks here in this summit to go into lens design in more detail. Hence, it is essential to include extra surfaces to balance aberrations and achieve the required multi-field transformation with adequate precision. Important now is to say that there is no evidence to suggest that flattening the lens eliminates this requirement. It should be also noted that there are mentions of configurations in the literature, on meta-lens in particular, in which fields overlap yet occupy different regions in the on the lens where we like to have the flat lens. Certainly, designing lens surfaces here in this area close to the image plane, here for the telecentric image site situation, benefits over lenses positioned near the stop, because we have some kind of separation here. These are just free samples, of course. However, this applies equally to both flat and thick lens surfaces, and this becomes clearly evident with the example of this cell phone camera lens system, where exactly this is used. To gain further insight, let's consider the design of a beam expander. In this case, an initial lens is necessary to transform the incoming planar phase into either a converging or diverging spherical phase. Here the diverging case is demonstrated. A second lens is utilized to collimate the incoming light. Thus the use of two lenses is mandatory. Again, flattening the lens does not change that outcome. Based on these observations and additional factors, we arrive at the subsequent conclusions about capabilities of flat lenses. For sure, flat lenses reduce both the thickness and the weight of lenses. That's what we need to expect, and that is a major reason we do it. The slim profile of flat lenses might enable more options for decreasing the spacing between lens surfaces, which is illustrated here. Let's assume these are two surfaces. Then we go closer and closer and closer. Then there is some point where we need to stop. Whereas when the lenses are flat, we are more flexible. How close we really can go depends, of course, on other factors too. But from a pure geometric point of view, we have this option. The fabrication methods for flat lenses vary from those for traditional lenses, which may offer benefits in specific scenarios, in particular for integrating different options, electronic and optics, that's for sure. Flat lenses could provide new opportunities for switchable lenses, which is related to here, to the fabrication. There's another interesting thing. Replacing thick lens surfaces with flat surfaces changes the aberration dynamics in the system, which may enhance aberration correction possibilities based on the particular scenario. Remember, employing diffractive lenses which exhibit strong and opposing chromatic aberrations to counteract the chromatic aberrations of smooth lens surfaces, that means material dispersion, serves as a well-documented instance of this potential. Some characteristics of flat lenses, such as its polarization-sensitive function, may be considered beneficial or sometimes detrimental, depending on their use. At the end of this webinar, I give you an example of their usage. It's also important to understand that there is no evidence to suggest that flat lenses, including meta-lenses, reduce the total length of the system or the number of lens surfaces in optical systems beyond what is possible with aspherical and freeform surfaces, except the previously mentioned observation about the slim profile. That, of course, gives some extra options here. We come to a summary of this understanding that ultimately flat lenses offer a notable and intriguing addition to the array of tools for optical design. Very interesting. The usefulness of flat lenses, on the other hand, changes significantly based on the context of the application. And so it is crucial to integrate flat lens technology into lens design workflows to fully comprehend and fully utilize their capabilities. To say it a little bit differently, it is time to practically evaluate the potential of flat lenses in application scenarios, in real-world application scenarios, and move beyond mere theoretical debates. From my point of view, the following two workflows are of paramount importance. Workflow number one: carry out the structural design of a flat lens based on a specified functional lens. So you start with a functional lens specification. That's what kind of wavefront transformation you like to achieve. Then you design it, evaluate the performance of the lens, and then you collect and export lens data for manufacturing needs. For example, here, DS2 export, as we do it in virtual fusion for meta lenses. Second workflow: substitute a thick lens surface with a flat lens in an existing system. Then assess the functioning of the resulting system that incorporates the flat lens, and also in the third step then facilitate system optimization. I like to emphasize that incorporation of flat lenses into lens design workflows requires substantial advances in both the theoretical underpinnings and the implementation of optics software. It is not just introducing data interfaces across various software products that does not offer the required solution. In my opinion, in our opinion at LightTrends, three essential objectives must be achieved in the advancement of optics software, and that is: first, develop efficient and user-friendly design algorithms for flat lenses, enable the simulation of lens systems that incorporate flat lenses with adequate accuracy and speed, and facilitate the optimization of optical systems that incorporate flat lenses. At LightTrends, we are committed to enhancing flat lens features of our software virtual fusion to meet these objectives this year. In this webinar, I will focus on the first objective. There is another webinar next week, and this webinar is titled "Let's Talk About Meta Lenses," during which I will concentrate on the second and the third objective. Let's now turn our attention to the design algorithms. That means to the first point. Our exploration of flat optics design begins by examining how a plane wave is transformed from an input direction to a signal direction vector. Of course, we base it on the design equation, as I discussed before, for this kind of situation. And solving the design equation for these parameters here, input 0 degrees, output minus 30 degrees, results in a planar surface, which is, of course, an entirely expected outcome. It's just a surface of a prism, probably, which we have done before. Not probably, it is a prism, of course. The dashed lines represent the incident beam, and the region where this beam intersects the planar interface is highlighted in blue. Reducing the width of this region clearly shows that the interface is available only in a minor portion of the required aperture in the whole area here. Hence, additional surfaces are required to achieve a flat solution. So we need something here in these blue areas also. Fortunately, in addition to our basic design equation where we say delta psi should be 0, there exists an alternative solution, or a set of alternative solutions, where I replace the 0 by a multiple of 2 pi. So JDM is an integer. And this is possible because for phase values, a multiple of 2 pi is identical to 0 because of Euler's equations. The parameter delta m can be used to control the spacing between these solutions with a setting of delta m equal 1, resulting in the smallest spacing. So we have here, for example, different solutions for delta m equal 400, which are just parallel planes here, and delta m equal 200 is shown here. Now, based on the input direction, here for this case 0 degree, we can now start, for example, here or here with an input direction and construct a triangle which is using this first plane. And then we follow this successively and construct with additional planes this grating. So that means by this kind of construction process, we get a grating, a surface grating, which is transforming the deflection of the incident light to another one. Here's another example, 40 degrees, this direction, this the angle, this triangle. So it means this approach yields analytical formulas for the grating profile tailored to any given pair of input and output directions. The choice of delta m determines the height and period of the grating, with delta m equal 1 achieving the minimum value for both. The method can be applied to both the transmission and reflection scenarios. And of course, we have implemented this kind of grating designs in our software Virtual Lab Fusion. We now proceed to discuss the broader scenario that involves transforming both planar and spherical phase profiles. So let's again start with our determination of our functional lens, so input and output phase. Then we design our surface by solving this equation. That's the thickness of the lens. We like to make it thinner. Then we need more solutions. So we proceed here with the same way as we did before to incorporate additional surfaces. The flat lens design procedure now, so we have here the surfaces, and by the way, I like to mention that these surfaces are not just shifted surfaces, they are all a little bit different. In a real world example, that is much more obvious than here in this one to illustrate it. Now, the lens design procedure now starts with establishing a baseline, identifying the points where it intersects with the surfaces. So that means we start with the baseline, and then we identify the intersection points of this baseline, which can be everywhere, by the way, with these surfaces. At each intersection point, a straight line is initiated following the local direction of the input direction vector, given by the gradient of the input phase. And the point where it intersects is the next surface is calculated. And we can follow this over across the entire lens aperture, and by this we can construct the zones of the flat lens. So this is a procedure, and this concept enables the creation of a quick and flexible algorithm for the design of flat lens surfaces. This method is applicable to scenarios involving both transmission and reflection, and is effective regardless of whether we have rotational symmetry is assumed or not. That means also in free-form surface situations, this technique can be applied. This design algorithm has been integrated already in our proprietary Virtual Lab Fusion software and is planned for a release in this year as well. Let's now consider some sample applications of the design algorithm I just have shown. They are configured for illustrative purposes only. Here we have an example of a focusing lens with a baseline, the construction of the zones for delta m equal 2. The choice delta m equal 2 for this kind of situation leads to a thickness of the flat lens of 2 micrometer. Now here's a collimating lens with delta m equal 50. Here the direction are a little bit unparalleled because the light comes from a spherical wave. It's collimated. The resulting profile, and here it's interesting to see the design leads to a noticeable tilt in the side walls of the profile, and 50 micrometer. Now let's go to an imaging lens. Example here for delta m equal 5. An input point is imaged to an output point, just 1 to 1 here, just for illustration. So here is the result for delta m equal 5. Now comes the point. If the outer zones here become too narrow for fabrication or other constraints, then this algorithm is flexible, enabling the setting of a minimum lateral dimension for the zones. So I can skip some of these surfaces, and by this I can enlarge these zones while allowing an increase in the local height. So I get this result. So here the zones are almost constant, but the height is increasing. And this approach has effectively implemented in the flat lenses used in Meta's Oculus VR glasses. You can see it here. The zones have constant size, almost constant size, and the height must then go up. Design algorithm also allows for the distribution of lens power across both curved and flat lens surface profiles. To achieve this combination, we start with a curved baseline and follow the same procedure as that used for a straight baseline. So we do the same as before, but now we get this result. The examples illustrate our tailored design algorithm for flat lens height profiles. I like to mention that flat lenses which function according to their height profiles are commonly known as Fresnel lenses for large delta m's, diffractive lenses for delta m equal 1, and super zone diffractive lenses for small delta m but larger than 1. In particular, for diffractive lenses, the height profile may be discretized to facilitate fabrication via binary lithography techniques. That's the reason why sometimes these also are called as binary optics. That was very much in the beginning, in the 80s, the reason to call it binary optics. We will now explore the design of flat lenses that incorporate meta surfaces. In the process of designing a diffractive lens for visible light, a layer with a thickness of approximately 1 micrometer is obtained. We saw that already before. From the design construct of the diffractive lens with delta m equal 1, it is clear that this layer transforms the input to the output by causing a local phase delay that matches the phase difference delta psi, which we like, but in modulo 2 pi. The diffractive lens is realizing this local phase delay by a varying height profile. Alternatively, think about a layer with a constant thickness h, but with a refractive index n rho. So from the lens, from the surface profile, we go to an index modulated layer. This change in refractive index is the cause of the phase difference, which can be roughly formulated, approximately formulated, like that the phase difference is just proportional to the OPL, the optical path length, times KO, the wave vector, wave number. To continue the discussion, we consider the index distribution in a two-dimensional space. So we go from this here to this one. And next, suppose that the lateral variation here is implemented in a pixelated manner. That looks like this. So it's not continuous, it's pixelated, leading to that the delta psi is met by the constraint here just in pixels. So, and y, these are the positions, establishing an appropriate grid such as a Cartesian grid. The meta surfaces now utilize a high refractive index nanostructure for each pixel here. For example, this. Placed on the substrate with a lower refractive index to realize this phase delay or this corresponding refractive index. This concept requires that the distance between the pixels is less than the wavelength, and then the outcome yields a meta surface composed of appropriate nanostructures for each pixel. This approach has been recognized for a while here, and there are papers even before. But this was for visible light. But it has recently gained renewed interest. For insightful initial read, consider the paper by Lalande and Charbel. And I also like to mention another paper, informative tutorial by Yang Fan at colleagues. It is interesting and has a lot of references for further reading. Now, in practical terms, the fundamental steps involved in the design of metal lenses include the following steps. Select a nanostructure, often referred to as a meta-atom or a meta-cell, that matches the capabilities of your fabrication tools or your fabrication partners. So that's the first step. Find out what they can fabricate and what you can fabricate. You know what you need. You need some kind of nanostructure in the region of about 400 nanometers. So about 0.5 lambda is what you need about. And you need to know what you can do on this level, right? And this gives you an idea to go ahead. To start with this kind of more or less simple structures is, in my opinion, definitely the best way to start with. Then analyze the phase delay psi of the meta cell dependent on the structure parameters you have, for example, the height, the orientation, the size of what you have. Here's an example. Here we play with a diameter d of a pillar of some height, and we get a phase delay according to this curve here. Next step, take your calculated phase you need to achieve by your function lens in your pixel, map it on the parameters what you have from your calculation in step 2, and find the correct mapping to the parameter. And then assemble the meta lens by positioning the chosen meta cells at each location on your grid. And this describes the design method for meta services, and it's also what we do available, what we made available through Virtual Fusion software. This development is ongoing, of course. The user-friendliness is always under development and will be improved. And also here we will have features coming this year soon. Towards the conclusion of the webinar, we present a case study in which we exploit the polarization sensitivity of a meta lens constructed with rotated nanofins to achieve a switchable bifocal system. Here's the configuration. We position the meta lens ahead of a thick lens and aim to investigate how the focus of the combined lens varies based on the input polarization. That's what we like to do. To achieve that, the meta lens is simulated through a fast and approximate model which demonstrating the polarization sensitive focal length of the meta lens by overlooking some effects of stray light. This simulation method for the meta lens is compatible with the advanced fast system modeling features of the Virtual Fusion software, allowing for a quick simulation of this system in a few seconds. And that is not on a supercomputer, but just on a standard, more or less standard notebook. Initially, we present a simulation featuring a nanofin meta lens followed by a functional focusing lens. The simulation provides both the ray paths as the irradiances distributions on the detection planes here and here. To enhance the visibility here, we cannot use the same scaling. Here's the scaling for the focus. So we change the scaling for the second. It's here. So now we can also see the distribution here. So this is calculated in a few seconds. And now we change the right circular polarization to left circular polarized light. And you see how nicely the focus is switching by this. That's expected from the design of the meta lens. Switching to linear polarized light also works, no problem. And you see that then both foci are switched on. Now, next we replace the functional lens by a spherical lens, which was calculated just by the lens meter equation. Then we have significant spherical aberrations in the system, which shift the focus points, the focal points in this assembly, which includes the meta lens and the spherical lens. It is notable that we can model aberrations by the lens and the meta lens all in combination and get a combined result. Here for the white circular polarized light, the point is shifted from here to about here. And then when we go to left circular polarized light, we have just defocus from the spherical aberrations. To minimize aberration, we substitute the spherical lens with an aspherical lens, modeled or calculated by our surface design method. And now we get results that are close to the functional lens. So for this completely meta lens and the thick lens here, in this combination we get a nice focus here, and here a little bit aberrations, but very, very small ones. And then linear polarized light, we get the two spots as hoped for. Now, we will delve deeper into the integration of meta lenses with lens systems. That was just an appetizer, to say it this way. The lens systems in our next webinar for next week at May of 29, and I hope to see your continued participation. To wrap up today's webinar, I will reiterate the statements I made earlier. Flat lenses represent a significant and fascinating enhancement to the toolkit available for optical design, particularly in the fields of imaging and illumination. Ultimately, it is essential to incorporate flat lens technology finally into lens design workflows to fully grasp and take advantage of their potential. At Lightwinds, we are committed to significant advancement in realizing this important objective through our software virtual fusion in 2024. I just stay here tuned for more updates. Stay tuned for more updates, and I like to thank you for your attention.
Thank you so much, Frank, for joining us to detail the future of flat lens design. Before we wrap up here, to everyone in the audience, if you haven't already, you can type your questions and comments into the Summit chat box. Do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Optical Design Summit. Thank you all so much for joining us.